Welcome to Puzzles to Exercise the Mind, Lesson 1. We're going to cover several different puzzles here. They're not necessarily related, and that'll be typical of this series. So let's get started with the first puzzle. What is the sum of the numbers from 1 to 100? That's our first puzzle, and we can do this fairly easy today. There's actually a formula which I'm going to describe in a few minutes, but we could do it with a calculator manually. We could do it with a spreadsheet sort of manually where we list all the numbers from 1 to 100 and then sum them up. But this puzzle was first given by a grade school teacher to his students to keep them busy in the 1700s. And to the surprise of the teacher, one of the students quickly came back with the answer. It turned out the student was would become eventually one of the greatest mathematicians of all time. His name was Carl Friedrich Gauss. He was born in 1777 and lived until 1855. So he was 7 years old at the time of this story concerning solving the puzzle. As I say, he went on to become a great mathematician, an astronomer, also a physicist. And his talent was recognized fairly early, and he was given an education. He eventually even got a PhD, and as I say, he went on to do many great things after that. Before we get to the solution of the puzzle, let's have a little bit of background on Gauss. There's a painting of him on the right, and I have some information here from Wikipedia. He was born in Brunswick, which is now part of Lower Saxony in Germany. His family was of relatively low social status. His father worked as a butcher, bricklayer, gardener, and treasurer of a death benefit fund. Gauss characterized his father as honorable and respected, but rough and dominating at home. His father was experienced in writing and calculating, which I guess those analytic skills passed on to his son. And they also note here, excuse me, in the Wikipedia article that his mother, Dorothea, was nearly illiterate. So let's see how Gauss solved the problem. We know he did the problem quickly, and this is how he explained what he had done to his teacher, and now that's been passed down for many centuries actually. This story. So he wrote down the numbers from 1 to 100. Maybe he even visualized this in his head, but basically took the numbers from 1 to 100 and then wrote them in reverse order, 1, 2, 3, all the way back down to 100, and put them next to each other. And so the key is seeing that 1 plus 100 is 101, and 2 plus 99 is 101, and all the way down. So basically, you're adding the numbers from 1 to 100 twice, but the trick is that you're getting the same number if you do the addition in this order here. So you get 101 100 times, and since you've added the numbers from 1 to 100 twice, you have to divide by 2. So 2 goes into 100, and you have 50 times 101, and that's fairly easy multiplication, and you get 5,050. So that's how he did it. It's quite interesting for someone at 7 years old, but as we know, he was quite an intellect, and he went well beyond this. In fact, as a teenager, he solved the problem of constructing a 17-sided polygon, regular polygon with equal angles and equal sides, and that problem was unsolved for, I think, but going back to the Greeks, so some almost 2,000 years that the problem was unsolved, and he solved it. He didn't just solve that; he solved, in general, what polygons, could be constructed with straight edge and compass. So, yet another feat at a young age, and he went even beyond that to discover many new things in math, physics, astronomy. So we have here the general problem, summing the numbers from 1 to n, where n is a whole number. So n could be 100 as we showed before, but it could be 101, it could be an even or odd number, it doesn't matter. And you just list the numbers in reverse order, as we've done here in the second row, and then when you add them, you get 1 plus n plus 1, n plus 1, and so forth. So you get n plus 1 n times, and since you've listed the numbers twice here, you have to divide by 2. So the sum of the numbers from 1 to n is n times n plus 1 divided by 2. So let's just show that it works for an odd number. If we put in 11 here, we get 11 times 12. You divide 2 into the 12, it's 6. 6 times 11 is 66. So you may want to try that on a calculator or a spreadsheet, but that should be the correct answer. So the nice part here is, even with a calculator or a spreadsheet or a computer, if you try to do it this way, it would take a long time. If, say, you had n equals 1,000,000, even though computers are very fast, why, go use that computing power when you can just plug 1,000,000 into here and then just do a division and one multiplication to get your answer. So, and there are other formulas. We won't talk about them here today, but there's formulas for 1 squared plus 2 squared plus 3 squared all the way up to n squared. So you can add up squares and get a formula in cubes and so forth. There's different formulas for adding sums where you can simplify the process. Okay, puzzle number 2. We have a drone, flying drone, and 2 trains. It's our entities in this puzzle. And this mini drone is flying between the 2 trains. Each train is traveling towards each other at 30 miles per hour. And the mini drone starts at the front of one train, travels to the front of the other train, and then turns around immediately with no lost time and flies back towards the other train. And it keeps going back and forth between the 2 trains until the trains collide. Let's just assume there aren't any people in the trains. Nobody's going to get hurt. It's model trains, for maybe. And the question is, if the mini drone is flying at 75 miles per hour, and again, it loses no time when it makes the turn and goes back towards the other train, and the trains are separated by 180 miles, what is the distance that the mini drone travels until the moment the 2 trains collide with each other? So I've drawn the situation here at the bottom of the slide here. We have a train going 30 miles per hour this way and a train going 30 miles per hour this way. So one key observation is this distance is closing at the combined speed of 60 miles per hour. So it's getting smaller at 60 miles per hour. And how long would it take given that you have 180 miles between these 2 trains when you start, how long would it take for the trains to collide? And that would be 3 hours, since they're approaching each other collectively at 60 miles per hour. So there's 3 hours, and during that time we have this drone going from here to here, and then of course this train gets closer and it comes back here and then here, and there's basically an infinite series, but we don't need to compute the infinite series. We just need to know that the trains are going to collide in 3 hours. The mini drone is traveling at 75 miles per hour, so it is traveling for a time of 3 hours. So you just need to multiply, and we get 225 miles is the distance traveled by the mini drone before the 2 trains collide. So this is a classic puzzle. I've seen it several times in different forms. Sometimes they use, instead of a mini drone, let's just say a fly, but I thought a mini drone was maybe a little more up to date in terms of technology and something that actually could go back and forth at a high speed between the trains. So there we have it. That's our second puzzle. Let's look at another puzzle. Puzzle number 3. So in a room, we have 99 right-handers and 1 left-hander for a total of 100 people. So the percentage of right-handers would be 99 divided by 100. You get 0.99 or 99%. And the puzzle is to find out how many right-handers need to be removed from the room to take the percentage of right-handers in the room down to 98%. As a general rule, if you have a puzzle where you can kind of test some cases or basically get your hands dirty with some calculations, that usually is a good way to get started. So that's what we'll do here. We start with 99 right-handers, 1 left-hander. Maybe I should have put the total number here. It's pretty easy to add. So we get, as I said before, 99 divided by 100, so 99.99 or 99%. So we remove 1 right-hander, and here's the trick. Here's where you kind of see where you can go wrong. You have it's true you have 98 right-handers and 1 left-hander, but you only have 99 people in the room now, so you have to divide 98 by 99, and you get 0.9898. It actually repeats indefinitely. I just cut it off here, and then you remove 1 more right-hander, and so you have 98 people in the room, and you have to divide 97 by 98, and you just drop down a little bit in the 4th decimal place. Remove 1 more person, and you go down a little bit. So it looks like if you thought you just removing 1 person was the answer, which was kind of my first, very quick reaction, that's not right. We want to get down to exactly 0.98. So we could continue this list here, and if you had a spreadsheet, you would actually get down to 50 before you get to that. But there's a way of doing it using some basic algebra, and I'll show you that on the next slide. So how do we solve this problem using algebra? I took over our preliminary calculations, these first several rows from the last slide, and then I put it down in generic form here. So, for example, this column here is 99 minus x. It's first x is 0, then x is 1. Here we get 98. X is 2. Here we get 97. And so forth. So this 99 minus x just represents x represents how many people are removed, how many right-handers are being removed from the room. The number of left-handers remains constant. It's just 1. We're not removing any of them. And then the calculation here is we want this to be 0.98 or 98%. And what is the what are we dividing here? So we're dividing the number of right-handers, so that would be 99 minus x. For example, let's take this one here. So it would be 97 minus 2, and then it's 2 less than the number of total people we have, or x in general minus the total number. So this is the fraction here, 99 minus x divided by 100 minus x. And if you do that, if you solve for x, which we'll show here just as a kind of a refresher, if you haven't done a whole lot of algebra lately, we'll go through this slowly. So we want to solve this equation here for x. First thing we do is we multiply both sides by 100 minus x. And you can always do that whenever you have an equality. You can multiply both sides by the same thing, and you still have equality here. So when you multiply 100 minus x times this side, of course it cancels this out. That's why we're doing it. And then 100 minus x times this side here, we get 0.98 times 100 minus x. Then the left side we leave as it is, but then here we multiply through. So 0.98 times 100 is 98. And then just 0.98 times x. So we still have the minus sign here. Then we subtract the 98 from the 99 and we get 1. Bring this, and again, when you have an equality, you could subtract the same thing from both sides. We'll do that. So I'm kind of combining two steps here. Subtract the 98 from the 99, get 1, and then add x to this side, because you can always add the same thing to both sides when you have an equality. And of course, 1 plus or minus 0.98 is 0.02. And 0.02 is just 2 over 100 or 1 over 50. And then you multiply both sides by 50 and we get x equals 50. So we need to remove 50 right-handers to get the probability or the percentage down to the fraction down to 0.98, or the percentage, 98%. So there we have it. It's a bit of a interesting problem, a little bit of review here. I'll try not to get into algebra that's too much more complicated here. We might do a few second degree equations, but we'll review that as needed when we get to that. Let's look at our next puzzle. This one's a bit complex. It'll take several slides to talk about the solution. I got it from a book, Arithmetical, Geometrical, and Combinatorial Puzzles from Japan. The English version was published by the American Mathematical Society. My understanding is the puzzles were initially published in a monthly magazine by this author here, and then the readers would propose solutions and the author would discuss the solutions in the next issue of the magazine. So here's the puzzle. We have consecutive whole numbers, 1, 2, 3, 4, so on. So we always start with 1, and we want to partition them into several groups, one or more groups, such that the largest number in the group equals the sum of the smaller numbers in the group. So that the implication is that you have at least 3 numbers in each group, such that you have 2 smaller numbers at least, and that add up to the larger number. You could have more. You could have 5 smaller numbers that add up to the larger number, but you need to have at least 3 numbers in the group. And we're going to look at the problem for different cases here, 10, 12, 14, 16. In some of the cases, it's not possible to get a solution, and we'll prove why that's the case. And just to give you a concrete example here, if we take n equals 3, we would have just the need for one group, where we add the 2 smaller numbers, 1 plus 2, and we get the larger number in the group 3. So that's a simple case. If you look at 4, it's not going to work, because if you put 3 numbers in one group, you're left with 1 number, and there's no way you can get 2 smaller numbers to add to that number, because you've run out of numbers in that case. Same thing for 5. That won't work. 6 doesn't work either, not because you can't break it into groups of 3 or larger, but you just can't find any way of getting the smaller numbers to add to the large numbers. So you may want to pause the video here and try it for 6, just to get a little bit of experience before we go to the solution in the next slide. As I already mentioned, the problem has to have at least 3 numbers in each group, and we're not allowing single groups with a single member in it. And as I noted, the problem has no solution for n equals 4 or 5. For 6, if you tried it, that doesn't work either. We do have a condition that will help us eliminate some cases. Since the largest number in each group equals the sum of the other 2 numbers in the group, it must be that the sum of the largest numbers from each of the groups equals half the sum of all the numbers in our sequence. This implies that some of the numbers in our sequence must be even for the groupings to be possible. So for example, if we take n equals 10, We add that up using our formula that we derived earlier. We get 55 as the sum. That's an odd number, so from our analysis up here, that means that there's no possible solution for n equals 10. If we try n equals 14, we take the sum of the numbers from 1 to 14, we get 14 times 15 divided by 2, and that's 7 times 15, which is 105. So again, there's no solution in this case either. So you can eliminate some of the possible values of n. You might want to try some other ones, I'm just doing even numbers, but it's possible to have a solution for an odd number in our sequence. So you might want to try 9 or 11 and see if we can exclude any of those. For some values of n beyond just the simple example n equals 3, we can get solutions, and we'll see that in the following slides. I'll give you one. Actually, I'll give you one answer. I'll do another one, and then I'll leave an open issue for you to try yet a third problem. So let's see if we can get a solution for n equals 12. First thing is to check to see if the sum of the first 12 integers is even. We can use our formula n times n plus 1 over 2. Putting in n equals 12, and we get 12 times 13 divided by 2. 2 goes into 12 6. And so we get 78. That's even. So we're not able to exclude n equals 12 as having a solution. It doesn't necessarily guarantee that, as far as I know. That's actually an open problem, which I'll mention later. So we also know that the sum of the largest numbers in the groups has to be 39. Let's see if we can make use of that. If there are 3 groups, in other words, if we divided the numbers 1 to 12 into 3 different groups, the best we could do in terms of the largest number would be 10, 11, and 12. So if the largest number in each of the 3 potential groups was 10, 11, and 12, we would only get 33, and that's less than 39. So if there is a solution, it's more than 3 groups. What about 5 or more groups? Well, if there were 5 groups, then we only have 12 numbers, and we need at least 3 for each group. So in order to have 5, we would need at least 15 numbers. So 5 doesn't work. That's out. So if there is a solution, we've excluded 3 and we've excluded 5, and more than 5 and less than 3 isn't going to work either. So it looks like 4 would be the number of groups we would need. We would need to break this into the numbers 1 to 12 into 4 groups if there is a solution. And we can experiment. If the largest number in each one of those 4 groups has to equal 39, so we can play around with the numbers from 1 to 12 and see if we get anything that adds up to 39. And maybe the obvious thing would be to take what we have here. We know this fell short, and maybe just take 6 and see if that works. And it does. Groups with largest number 12, 11, and 10 add up, and 6 add up to 39. Now the next part is where you kind of need to roll up your sleeves and get dirty, a little bit dirty, and see what can work here. And there's, I guess, no real easy way to explain it other than just saying you kind of need to work through it. And I'll give you the answer. Let's just check. This will also give you a feel for exactly what's being asked. Hopefully you've figured that out by now, but if not, let's emphasize it through this example. So if you play around with the numbers from 1 to 12 and you start putting them into 4 groups, obviously if there's 4 groups, they're each going to have 3 to add up to 12. So I have here in the first group 12, 9, and 3. So 9 and 3 adds to 12. So that condition holds here. Then 11, 7, and 4. And that 7 and 4 gives you 11. So that works. And then 8 and 2. gives you 10, so that works also. And then the final group is 6, 5, and 1, and the 5 and 1 adds up to 6. So we actually got a solution for n equals 12. Okay, let's try n equals 16. As we've done before, we need to check to make sure the sum of the numbers from 1 to 16 is an even number. We use our formula again here. It would be 16 times 17 divided by 2. And I just worked it out for you here, but it's an even number. So we know a solution is possible. And we divide this by 2, we get 68. So we know the sum of the largest numbers in each group is 68. There's different possibilities. Actually, there's more than one solution. At least I found two, but I will show you one and then leave the other one as an exercise. Well, let's work on one of them here. So one possibility is to use 4 groups of size 3. That'll give us 12 numbers. And then that would leave 4 more, so we'd have a group of size 4. And we can play around. So that alone is a little bit of experimentation just to come up with that. And then if we look at the largest numbers in each group, they need that up to 68. So I fooled around with the numbers. We're starting with some of the larger ones here. And I tried 14, 15, 13, 14, 15, and 16, and what was left was 50. This was 58, and what was left is 10. So I figured let's go with that and see if we can find 4 groups of size 3 and 1 group of size 4, such that the smaller numbers in each one of these groups adds up to these numbers here. So I'll show you a little bit of how I experimented on the next slide, but there's at least, as I mentioned, there's at least one other solution using groups of size, 4 groups of size 3 and 1 group of size 4. What's different is the largest numbers are different in that partitioning, and I'll leave that as a problem for you to try. But let me show you what I did in terms of finding a solution here on the next slide. I used a spreadsheet. Okay, so here's what I did, and hopefully you have some experience with spreadsheets. This isn't a particularly hard application of a spreadsheet. What I took the numbers that I wanted to experiment with as being the largest numbers in the group. So I put those in a column in the spreadsheet, and then I basically did a sum here. So I took these numbers, lift this off to the side, and then took these numbers in each row and then added those up. So you could put a sum of these and put it in another cell here and another cell here. And then it makes it easier for you to just, put some numbers in the different cells and see if the sums add up to our goal of these numbers here. And you can play around with the numbers. So if you initially put 4 here and 5 here, you would see you weren't adding up to what you wanted, and you can just flip them around a bit. So I found that to be, at least for a relatively small number, I found that to be a good methodology for experimenting. So let's just double check that everything works out. First, we want to make sure we have all our numbers. So we have 13 to 16. And then we have 11 and 12 and 10. So we have all the double digit numbers. Then we have 1, 2, 3, 4, 5, 6, 7, 8. So we have all the numbers from 1 to 16. So that's an easy thing to miss. You might think you have a solution, then you realize you either repeated a number or you missed a number. Then the last step, of course, is the important part. The smaller numbers need to add up to the bigger number, the largest number in each group. So 4 and 12, what works out? 1, 3 is 4, plus 11 is 15. 5 and 9 is 14. 6 and 7 is 13. 2 and 8 is 10. So there you have it. We have one solution to our problem for n equals 16. So we have some open problems related to our partitioning puzzle. The first one is we know from our analysis that if the sum of the integers up to n is odd, then there can't be a solution. But the question is, well, what if they add up to an even number? Are there cases where we can't find a solution? We looked at 12 and 16, and we did find a solution. But maybe there are cases where this adds up to an even number and you still can't get a solution. And so that would be one thing to look at. Then along the same line of thinking, is there any pattern as to when you have a solution and when you don't have a solution? We know for n equals the sum from 1 equals n equals an odd number, we don't have a solution. But is there something more specific that we can say? Is it like I say here for this first one? Is it if it doesn't work when you sum the even numbers? Is there some other condition that would allow you to just look at the number n and say, okay, I know this. There's no solution in this case here. And then beyond that, the obvious question is, well, when there is a solution, when we can figure out if there's a condition, when we can determine that there is a solution, how do you go about doing that? Is it just ad hoc? Do you just have to keep searching exhaustively, or is there some algorithm or methodology that we can break things down into steps where you don't have to look at every possible solution and you can come to an answer in less than the complete search through all possible solutions? So that's, I think, an interesting problem. I'm not aware of any solutions. Like I said, this problem came from a book, and they just gave the one answer for n equals 12 and a little bit of explanation, but they didn't mention any of the proposed solutions from the readers of the magazine where the puzzle was first published. So there may be something out there, there may not be. In fact, if you're interested in this, you might want to do some web searches on this problem, or maybe even one of the AI programs, and see if you get any useful information back. Okay, so these are some open problems. Then there's the other one is that for the case n equals 16, I mentioned that there's another solution with the same group sizes but different largest numbers in each group. And I'll give you the answer to at least the one I found, I'll give you the answer to that at the end of this lesson. There may be even more than just one additional solution, which would be great if you can find that. Maybe put something in the comments to this video and share your solution. So let's go on and continue. We have a few more problems. And I want to talk a little bit about Kaprekar's constant. This isn't a puzzle, but more just of a tidbit, something of interest, an interesting thing I never had seen until recently. But it's basically an algorithm that always converges to the same number. Let's walk through it and see what I mean. So you take a number like 218, a four-digit number, and what you do is you put the digits in decreasing order. So you 8, 7, 2, 1, and then you put them in increasing order, 1, 2, 7, 8, and you subtract. And you get this number here. Then you do it again, and these are already in the right descending order, but you put them in ascending order, and you subtract. Then you do this again, so you get 9, 9, 6, 3. Then you put them in ascending order, you subtract. You get 6, 6. Putting this in descending order, 6, 6, 4, 2. And then ascending order, 2, 4, 6, 6. You subtract, and then something weird happens. You get the ascending order. You subtract, and you get 6, 1, 7, 4. And you do it again. And of course, when you do this, and you get the same two numbers again, 6, 1, 7, 4. So maybe not so interesting because we just did it for one number. But the interesting part is you can take any four-digit number with at least two distinct digits. In other words, you can't use 0000 or 1111 or 2, with all the 4 digits repeat. Obviously there you're going to subtract, excuse me, you subtract and you're going to get 0. But as long as 2 of the digits are different, 1, 2, 1, 2, that'll work. You'll converge to this 6, 1, 7. That alone is interesting, but it always converges within 7 iterations. So kind of a strange fact. This Kaprekar was the person who discovered it. There's also a similar constant for 3-digit numbers. Again, it was the same condition as long as you don't have 111 or 333 or the repeated 3-digit number. As long as 2 of the numbers are different, 3 digits, you get the same. You get a similar pattern, I should say. It'll converge to another number. I won't tell you what it is. I'm sure you'll figure it out if you try a few numbers. I'll leave you the pleasure of finding that. And there's also a website which you can type in. It's a calculator, so you can. You don't even need to do these. If you don't believe me here, you can try your own 4-digit numbers, and this will show you the convergence. And I believe you can put 3-digit numbers in there too. So that's an online calculator you can make use of. The next puzzle is it comes from a letter that was sent from a friend of Albert Einstein, a psychologist, Max Wertheimer, in 1934. I guess he was sort of a hobbyist in terms of puzzles and whatnot. He figured Albert Einstein could figure it out. So this is what he sent in the letter. An old Clattery auto is to drive a stretch of 2 miles up and down a hill. Because the car is old, it cannot drive the first mile any faster than 15 miles an hour. So the question posed to Albert Einstein was, how fast does the car need to drive the second mile going downhill? Of course, it could go a little bit faster in order to obtain an average speed for the whole distance, 2 miles, of 30 miles per hour. So it's when you start looking at this, it seems simple, but when you work through the details, you'll see it's rather interesting. So we'll get back to this in a bit. Here's the alternate solution I came up with to our partitioning problem. Again, I used the spreadsheet to fool around with the numbers a little bit, but I switched the largest numbers and I added them up, and they again came to, let's see, 30, 15, 45, and 23. So they came to 68 again. Remember, that was the requirement. So first I found the prospective largest numbers that added up to 68, and then I fooled around with the numbers, the remaining numbers, and I managed to get them all to add up to these set of numbers here. So we have 3 and 13 is 16, 5 and 10, 15, 6 and 8, 1 and 4 it's 5, and 7 is 12, and then 2 and 9 is 11. And we can see we have all the numbers here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is another valid solution. I don't know if there's more. If there may be. I think it would need to be in this format here where you have 4 groups of 3 and 1 group of 4. And I didn't really search beyond this, so you may want to see if you can find another solution. Okay, so let's look at the solution to the problem posed to Albert Einstein. Let's just look at the car going uphill at 15 miles per hour. That comes to 15 miles per 60 minutes. I'm just substituting 60 minutes for 1 hour. Then if you divide the 15 down into the 60, you get 4 minutes. So in other words, the car going uphill can travel 1 mile in 4 minutes, and in fact, that's how far it had to go to go up to the top of the hill. So it was a 4-minute trip for the car to get up to the top of the hill. The next thing is to look at what it would take to average 30 miles per hour over the entire trip, given that we've already spent the 4 minutes here. So that's the catch to the puzzle. If you take 30 miles per hour, then that's 30 miles over 60 minutes. And let's just leave this as 2 because we want to know how long it'll take to get 2. So we divide top and bottom by 15 and we get 2 miles per 4 minutes, which means it would take a total of 4 minutes to cover the 2 miles while averaging 30 miles per hour. But we've already burned the 4 minutes in the first part just going uphill. So basically you would have to go at the speed of light, or even faster, right? You would have to go at infinite speed to get back down the hill and still, not use any more than the 4 minutes you already wasted up here or used up here. So Einstein wrote back. I guess he didn't immediately see the contradiction in the puzzle, that it wasn't possible, but he writes back and says, not until calculating, so doing kind of what we did here, that I noticed that there is no time left for the way downhill. So kind of an interesting episode between Einstein and his psychologist friend.